this around the back like that. Is that right? Okay. Is this already on? Okay. All right, so the topic of my lectures is pretty similar to Luke's. I'm going to be focusing on a particular kind of compact binary, but the general picture is essentially the same. Everything I do is going to be on the blackboard. Maybe I'll show some numerical results on the last day on the projector. And if you have any questions, just interrupt me at any time. So we're looking at compact binaries. The notation I use is going to be a little bit different than Luke's. So I have one object of mass little m, another object of mass capital M, and they're orbiting around each other, emitting gravitational waves. The gravitational waves carry off energy and angular momentum, so the whole orbit shrinks. So say this is a separation, capital R. That separation is going to shrink with time. So the two objects get closer together. And eventually merge into a single object. Now these binaries all have very similar behavior in the sense that they're gradually inspiraling and then eventually merging. But they come in a few different varieties. I can draw the parameter space of compact binaries, which is the same parameter space that Luke drew, except my coordinates or my axes are flipped relative to his. So this is the orbital separation, and on the x-axis I have the ratio of the two masses. So if the two objects are widely separated, then their mutual gravity is weak and they're moving very slowly, and that's where post-Newtonian theory works. So that was the subject of Luke's lecture. So here you have objects that are very widely separated, orbiting around each other. And then as they in-spiral, they move down on this plot into this region down here. And this is where numerical relativity is used. So that's where we have two objects of roughly the same size, and they're close together, orbiting around each other. And the only way that we know how to solve the system accurately is by solving the fully nonlinear Einstein equation numerically. Then down here, you have one object much, much bigger than the other object. So capital M is much, much larger than little m. And this is going to be the focus of my lectures. So this is where we use something called self-force theory. And Luke gave you just a one-sentence introduction to that. The basic idea is this small object, as it's moving around, perturbs the space-time of the large object, and that perturbation then reacts back on the small object, exerting what's called a self-force. Now, these different types of binaries are observable by different detectors. The orbital frequency of a binary is roughly given by the Keplerian formula. Which is the square root of the total mass divided by the orbital separation cubed. So for simplicity, let's take capital R to be basically the same size as the total mass. Then this orbital frequency scales as 1 over the total mass. So the more massive your system, the smaller the frequency. So this is in geometrical units. If you want to restore the dimensionful quantities C and G, then this formula looks like C cubed over capital G and the total mass. So you can check that this has dimensions of 1 over time, like a frequency should. Now, ground-based detectors like LIGO and Virgo are sensitive to frequencies about 100 hertz. So if you rearrange this and solve for the total mass, so the total mass in this case is about 20 solar masses. It's about 20 times the size of our sun, or the mass of our sun. And since M and M must be at least as big as one solar mass in order to get a loud enough signal to detect, and the total of the two has to be of order a few tens of solar masses, we must have that the two masses are roughly the same size in order to be detected by a ground-based detector like LIGO or Virgo. So that means that LIGO and Virgo are restricted to this part of the parameter space, where the two masses are roughly equal size. But LISA, the space-based observatory that will be launched in the early 2030s, is sensitive to much, much smaller frequencies. Basically in the 10 to the minus 3 hertz. So for that, the total mass, again using this formula, is going to be about 10 to the 5 solar masses. So much, much more massive systems than what LIGO can detect. So LISA can detect comparable mass binaries where both masses are roughly the same size and they're both extremely large. So these are the kind of supermassive black holes at the center of galaxies. Also, LISA can move into this region on the far right, where the two masses are very unequal in size. So these systems over here are called EMRIs, which stands for extreme mass ratio in spirals. So the mass ratio in the system is extremely large. So here we can have the smaller object, basically one solar mass or a few tens of solar masses, and the larger object is a supermassive black hole. So these are really the kinds of systems I'm going to be discussing over the rest of these lectures. And let me, before describing how we model them, let me say why they're worth modeling, what's interesting about them. So EMRIs, here you have a supermassive black hole with some large mass and angular momentum, or spin. And then you have a smaller object zipping around with mass little m, and also a spin and potentially higher quadrupole moments. The massive black hole, again, is going to be one of the types of supermassive black holes at the center of a galaxy. And the smaller object is going to be a black hole or a neutron star. So we have black hole or neutron star orbiting around a black hole. This orbit is very, very intricate. So in general, it's highly eccentric. So it's zipping around on a very distorted ellipse. It's rapidly precessing, as I'm drawing here. It doesn't close in on itself. It's also inclined. So in a picture like this, it's not just moving in the plane, it's also coming in and out of the plane. And so it's called tri-periodic. That's because it has three frequencies. One is the frequency of the round and round motion going around the big black hole. One is the frequency of the in and out motion, the radial oscillation. And one is the frequency of the up and down motion. So you got three frequencies, say omega phi, omega r, and omega theta. Also, M spends a huge amount of time in kinds of orbits before it actually plunges into the big black hole. Basically, the inverse of the mass ratio, number of orbits. So 10 to the 5 orbits. In the very strong field region right around the big black hole. That's typically going to be about 1 year of real time. So because it's following these very eccentric, very intricate orbits and spending a lot of time near the big black hole, it's essentially acting as an incredibly precise probe of the space-time around the big black hole. So it's generating an extremely precise map of the space-time geometry around this black hole. So precise probe of the black hole geometry. Now, if we can detect the waveforms that come out of a system like this and accurately relate those waveforms back to the source that generated them, we can learn a lot of things. So from the Emery waveform, we can measure M and J, the parameters of the big black hole, very accurately. So to about 0.01% relative error. You can also measure the quadrupole moment of the big black hole. Slightly less accurately, but still fairly accurately, to about 0.1%. So with a combination of these two sets of data, we can test for deviations from the Kerr geometry of the black hole. So how many of you have studied or learned about the no-hair theorem in gravity? A small number. So the no-hair theorem tells you that if you have an isolated black hole that's stationary, so it's settled down after a long time, it is uniquely described by the Kerr geometry, by the Kerr spacetime. And in the Kerr spacetime, all of the multipole moments of the big black hole are uniquely determined just by the mass and spin of the black hole. So if we find that the quadrupole moment of the big black hole is related or doesn't satisfy that relationship with the mass and spin, that will tell us that we don't have the Kerr geometry and we don't have a Kerr black hole. So that means either general relativity is wrong, or we have some other exotic object that's ultra compact sitting there looking like a black hole, but actually isn't a black hole. So out of those two, I would say GR being wrong would be the much more likely scenario, but could be wrong about that. But the point is, measurements of Emery's are really the only experiment that has ever been proposed that would get you this kind of incredibly precise test of the no-hair theorem. So you can also measure other deviations from GR. There's a long list of things. And typically, the estimates for how well we can constrain these deviations with Emery's is at least one order of magnitude better than any other experiment, not just currently, but that has even been proposed. So these are really incredibly precise measurements we can make. You also learn about, based on the parameters of this system, and if we measure a few of them, we can start to assess how these systems tend to form, which will tell us about the astrophysics in the neighborhood of large black holes, what kind of things are going around them, and how those things interacting with each other. So we learn about fundamental things like whether GR is correct. We'll also learn astrophysics things. But to make all these measurements, we really need a very precise model of the Emery and of the waveform that comes out of it, because typically, if this is the strain measured by the detector, and it's a function of time, the Emery signal is going to be quite weak. So that's the Emery signal, and it's going to be buried under noise that's actually bigger than the signal. So we need a very accurate model to dig the true signal out from the noise. And the way that's done is with coherent filtering. We essentially integrate the entire data set against some template, the type of template that Luke mentioned. And the noise integrated against that template will just add up to 0 because the noise is random. But the integral of the template against the actual buried waveform will keep getting bigger and bigger as we integrate. So you get an integrated signal to noise that's bigger than 1, so it's detectable. But to do that kind of matched filtering and get those kinds of measurements, we need to model this waveform, in particular the phase, to much, much smaller than 1 radian error over the roughly 10 to the 5 orbits that we are observing. So over 10 to the 5 cycles of the gravitational wave. So that's an extremely stringent accuracy demand, much, much higher than other kinds of systems have. So then the question is, how can we model these systems that accurately? The standard tools, or at least some of the standard tools, don't work. So we can't use post-Newtonian theory. Because Emorys are highly relativistic. We're looking in the strong field region. The small object is moving around at relativistic speeds around the big black hole. So Emorys are highly relativistic. We also can't use numerical relativity. For a couple of reasons. First, because Emorys have very disparate length scales. So the numerical simulation has to resolve the tiny scale of the small object, as well as resolving the larger scale of the orbit and the scale of the outgoing waves. So that's extremely numerically expensive. But the bigger problem is really the huge number of orbits. So we need to model 10 to the 5 orbits, and that's way beyond what numerical relativity can do in any time in the foreseeable future. So they would typically do, say, 100 orbits maximum, and that would only be for comparable mass binaries, and it just gets harder for extreme mass ratio binaries. So what we use is what I called self-force theory, but it's theory. where we take the metric. Let me put a tilde on top of the metric when I'm referring to the exact metric of the full system. Is going to be equal to the big black hole's metric at leading order plus a small parameter epsilon times a first order metric perturbation plus epsilon squared times second order metric perturbation, and so on to all orders, where this epsilon you can think of being just the mass ratio. I will very often be a little bit sloppy, and I'll just think of the small mass itself being of order epsilon, thinking of the large mass as being of order 1. The large mass sets the overall scale. And I'll also be even sloppier and just set epsilon equal to 1 at the end of a calculation. That's just to avoid double counting and epsilon. So we can just think of epsilon as being a bookkeeping parameter that counts powers of the small mass. So the small mass will trace out which I'll call gamma. And I'll call the coordinates on that world line Z. So Z alpha is the coordinate description of the world line gamma. And traces out this world line in the background space-time of the large black hole. Yeah. Yeah. So he's asking the size of epsilon, 10 to the minus 5 or 10 to the minus 6. Yeah. What's that? Mm-hmm. Yeah, so the systems I'm describing are these systems where I have a supermassive black hole at the center of a galaxy and a stellar mass object orbiting around it. So at 0th order, this world line is a geodesic of the background space-time of the big black hole. Then at subleading orders, gamma will satisfy some equation of motion. Which I'll write as covariant derivative of Z alpha with respect to proper time is equal to some first order term plus some second order term, and so on to higher orders. So on the left-hand side here, this is the covariant acceleration in the black hole space-time. And everything on the right-hand side gets called a self-force. So the first question we want to ask is how high order do we need to go in this approximation? There's a fairly simple scaling argument that tells us the answer. So first we want to look at the overall time scale. Of the in-spiral. To get a sense for how long it lasts with respect to epsilon. So the kinetic energy, or the total energy of the small object, is going to have a rate of change. So E dot means rate of change with time. It has to be equal to the energy flux carried out of the system, so that means out to infinity or down into the black hole. And later, I think Luke and I will probably both talk about this energy flux, but it's basically the square of the time derivative of the metric perturbation. So since metric perturbation is of order epsilon, this means we have order epsilon squared. But the total energy of the small object's orbit is proportional to its own mass. So we can think of that as being order epsilon. So E dot over E is epsilon squared over epsilon, which means order epsilon. So this is the rate of change of the orbital energy relative to the magnitude of that energy. So this tells us the characteristic timescale of in-spiral. It's a time scale that's 1 over the rate of change. So E over E dot, which is 1 over epsilon. So in more physical things, it's m squared over little m. And this is called the radiation reaction time. And generally written just as TRR. Okay, so this is the overall timescale for the entire in-spiral. Now, what does that tell us about how accurately we need to know this equation of motion? Well, suppose we know that first order self-force, but we don't know the second order self-force. Then we have an error in that equation of motion. So let me just write a delta meaning error. That's of order epsilon squared, because we're omitting the second order term. That integrates up to an error in the trajectory itself, the world line of the small object. That's essentially epsilon squared times time squared. Just doing a very naive integration of bringing up two factors of time. So after an in-spiral time, or after a radiation reaction time, we have epsilon squared times 1 over epsilon squared, which is order epsilon to the 0. So if we omit the second order self-force, we have an error in our final, or in the trajectory of the particle that's of order epsilon to the 0. And remember, we need errors to be much, much smaller than 1 radian in the phase, whereas this is going to be exactly of order 1 radian in the motion, which translates into the phase as well. So since we need much, much less than 1 radian of error, we need to include the second order self-force, which tells us that we need to go to second order in perturbation theory. So most of what I talk about in these lectures, virtually everything, is going to be restricted to first order perturbation theory. But it's important to keep in mind that the ultimate goal is to extend everything to second order. And we don't think we would need to go to third order, because if you ignore the third order term in this expression and do the same analysis, it will be much, much smaller than 1 error in your phase at the end. Okay. So I'm going to try to cover quite a few topics relevant to Emery modeling. But obviously there's way too much to cover just in 5 lectures. So I'm going to give you a reference if you want to look up more details. There's a recent review by Lior Barak and myself that has an archive number of 1805.10385. So there are actually many reviews on this topic. This review in particular, though, is aimed at non-experts, so it would be the best place to start if you're not familiar with the topic. Okay, any questions so far? No? Okay, so I'm going to move on to perturbation theory. And what I say for the next little while really would not be restricted to Emery's, but we will ultimately apply it to Emery's. So I'm going to be looking at an expansion of this form, but you don't necessarily have a black hole metric at leading order. It's just some background metric. So we want to look at perturbation theory. So we consider that we have some metric that depends on a parameter epsilon. So in our case, epsilon will be the mass ratio, but for this whole section, you can think of epsilon as being any small quantity. We want to approximate this metric in the limit where that quantity is small. So where epsilon is much, much smaller than 1. And the first thing to consider is just a Taylor series. So we take our exact metric and we expand it in powers of epsilon. So the leading order piece is just the exact metric evaluated at epsilon equals 0. Then we have epsilon times the derivative of the metric with respect to epsilon, all evaluated at epsilon equals 0 again, and so forth to higher orders. So I'm going to call this leading order piece just G alpha beta with no tilde on top. This next piece I'll call H1 as I had it on the equation I erased here. And this bit without the epsilon squared, I'm going to call H2. The convention here is a little bit different than some other people's. Sometimes H2 will be defined without this 1/2 included in it. I'm including the 1/2 inside the H2. Now, let's define a total perturbation as the difference between the exact metric and the background metric. So define H alpha beta to be the exact metric minus the 0th order background metric, and that's going to be a sum over powers of epsilon times these perturbations H1, H2, H3, and so forth, where n runs from 1 to however high order you want to go. So the total metric is now the background plus this exact perturbation H. It satisfies the exact Einstein equation. Which I'll write as G alpha beta constructed from G tilde is equal to 8 pi T alpha beta. And then the main question is, what equations do these perturbations Hn satisfy? So how many of you have actually studied perturbation theory in GR to any extent? A few. Okay, so I'm going to go through this in some detail, which may be boring for the few of you who have studied it. But mostly I'll be following the presentation in the textbook by Wald. So to start, we will rewrite the Einstein field equation, which I'll write as EFE, as an exact equation for the total perturbation H alpha beta, rather than for H1, H2, H3, and so forth. So remember, the Einstein tensor is constructed from the Riemann tensor, so I'll put a tilde on top of the Riemann to indicate that it's the Riemann tensor of the exact spacetime. And remember that the Riemann tensor is defined from the commutator of covariant derivatives So again, the tilde will indicate that this covariant derivative is compatible with the exact metric G tilde. So we'll start by rewriting this covariant derivative on the exact spacetime in terms of the covariant derivative compatible with the background metric. And then from that, we'll build things up to eventually get to the Einstein tensor. So let's define a new object called C alpha beta gamma. Such that the difference between the two covariant derivatives acting on some vector is equal to this quantity C alpha beta gamma contracted into the vector. We can also write that as C alpha beta gamma is equal to the Christoffel symbol in the exact spacetime minus the Christoffel symbol in the background spacetime. So neither of the Christoffel symbols are defined as tensors individually, but the difference between two Christoffel symbols actually is well defined as a tensor. So this is a tensorial object. Now we'll show that this quantity can be written as 1/2 G tilde alpha mu covariant derivative on the background acting on the total metric perturbation another covariant derivative on the total metric perturbation And one last one. So let me just quickly prove that statement. So the proof in a local inertial frame of the background metric the Christoffel symbols defined with respect to that background metric are 0. So here I'm just choosing a particular coordinate system. So in that coordinate system, C alpha beta gamma is just given by the Christoffel symbols of the exact metric. So this is in this particular inertial frame. So then we can just write down the Christoffel symbols in terms of the exact metric. So here we just have partial derivatives, but we can actually replace those with covariant derivatives. And I'm assuming that all of you have studied GR to the extent that you would know this is the formula for Christoffel symbol. Is that right? Well, it is, okay. So this is just standard formula for Christoffel symbol of a metric. So now I'm going to replace those partial derivatives with covariant derivatives. And the reason I can do that is, again, because the Christoffel symbols of the background metric are 0 in this frame, which means the covariant derivatives with respect to the background metric are the same as the partial derivatives in this frame. Then I just need to do one more thing to recover the formula over there. And that is replace this exact metric with the metric perturbation. And I can do this because the covariant derivative without the tilde acting on the background metric is just 0. So if I replace this g tilde with g plus h, all the g terms are identically 0. You're left with just the h terms. So remember I said that C is a well-defined tensor. What I've got here is a well-defined tensor. So this result holds in any coordinate system, not just in the local inertial frame. This is a tensorial relationship. So next, Move over to this board. Next, we're going to use that result for C to get an equation for the Riemann tensor and then eventually for the Einstein tensor. So next, we'll show that the exact Riemann tensor of the exact spacetime is equal to the background Riemann tensor plus 2 times the covariant derivative acting on C plus 2 times a product of C with itself where here these square brackets denote anti-symmetrization. So if we have some tensor f alpha, and I take the square brackets of those two indices, that's 1/2 f alpha beta minus 1/2. Okay, so let's prove this relationship. Contracted with some vector is equal to the commutator of 2 covariant derivatives acting on that vector. And we can write the commutator in terms of the background covariant derivative, and that's C. This C is multiplied by some stuff, but you don't care what that stuff is because C is symmetric in the lower two indices, which means when you take the anti-symmetric combination, you get identically 0. So all I'm doing here is just replacing this covariant derivative with the tilde, with the covariant derivative on the background, plus C, and simplifying. And from this stage, it's just a matter of simplifying this expression to get up here. So this first term is just the Riemann term. of the background so this term here is this contracted into omega, and you'll have another term that's the product we see here contracted into omega. So I won't write down the details of this step, but it's just a matter of simplifying to get R tilde in terms of R and products of C and a covariant derivative of C. So from here, we can immediately write down the Ricci tensor. So next, the Ricci tensor is just the contraction of two of those indices on the Riemann tensor. So it's the background Ricci tensor plus these things involving C so this is the contraction of the first term there, and we have a similar thing for the second term to C alpha mu alpha C mu delta beta. So from this we can write down the Einstein equation. So the exact Einstein equation is given by R tilde alpha beta minus 1/2 G tilde alpha beta G tilde mu nu contracted into R tilde. So that is just the Einstein tensor of the exact spacetime. It's equal to 8 pi T alpha beta. So if we substitute this long expression for R tilde, then we have an exact expression for the Einstein equation in terms of the H's over here that appear in those C's. And then because of this inverse, it's not quite just in terms of the H's. The H is kind of embedded inside this inverse of the exact metric. So that part we do have to approximate. We need to approximate G tilde inverse which is given by the background metric inverse minus H alpha beta plus order H squared quantities. And you can easily work out to any order what combinations of H you need in order to make this the inverse of just G plus H. And then let me state a convention that indices are raised and lowered with the background metric, not with the full metric. So this H alpha beta I wrote is G alpha mu, G beta nu, H mu nu. Okay, so except for this approximation that's an expansion of the inverse metric, what we have here is an exact equation for the exact metric perturbation H. So now the next step is to expand that exact equation in powers of H, as we've started to do here. Yep. Which equation are you pointing at? This one here? Yep. These brackets? So that's this notation here. It's the anti-symmetric combination, so I take gamma delta, multiply by half, and I subtract the reverse. Gamma here, delta there. Okay? So let's expand the Einstein equation in powers of H alpha beta. So let me introduce a bit of notation. So for a tensor f of g plus h, so it's a tensor with any indices constructed from g plus h, I'm going to define the nth variation of that tensor to be 1 over n factorial dn d lambda n of f g plus lambda h, all evaluated at lambda equals 0. So all this notation means is that if I have some quantity involving g plus h, the nth variation is just a piece of that quantity that has n powers of h in it. So we can write f of g plus h as f of g plus delta f of h plus delta squared f of h, and so on, where this is linear in h, and this is quadratic in h, and so forth. So this is an expansion in nonlinearity. So as an example, g tilde alpha beta indices up is g alpha beta plus delta g alpha beta plus nonlinear terms, and this delta, as we saw over there, is just minus h alpha beta. So this is the linear piece of g tilde inverse, and we would have quadratic pieces, cubic pieces, and so forth. So let me just write one more thing before stopping for lunch. So we want to start with the expression we had for the Ricci tensor there. So the linear piece of the Ricci tensor, if we look there, this piece is going to be quadratic and higher order in H, because each of those C's had a piece of H in it. So remember, C, the form was like G tilde inverse times gradient of H. So this is going to be at least second order. This is 0th order because it's just a background. So the linearization of our tilde is going to be coming just from this middle term. The gradient is the background gradient, so it doesn't depend on H. So the linearization just passes through it. And we now have covariant derivative of the linear piece of C. So remember, C was like G tilde inverse grad H. We want to get just the linear piece. So if we take the linear piece, that means we're going to set this to be just the background. So it's just going to be G inverse gradient grad H, or variation of H, but that's just H, because we're looking just for the linear pieces of H, or the pieces that are linear in H. So if we carry this delta through, then we've got grad mu, grad alpha, H, nu, beta, plus grad mu, grad beta, H, nu, alpha. So this is carrying this gradient. Sorry, it's carrying this gradient in here. So we have two gradients acting on H. And then here we've got different combinations of those gradients. H, so grad mu, H alpha beta, minus grad alpha, grad mu, H nu beta, minus grad alpha, grad beta, H nu mu, plus grad alpha, grad nu, H mu beta. And you see this term is the same as this term, so they just cancel. And we can simplify this to be minus a half box H alpha beta minus a half grad alpha grad beta acting on H, where this H is the trace of H with respect to the background metric. And one more term, grad mu, grad alpha, H beta mu, where these indices are symmetrized. So round brackets indicate the symmetric combination, just like square brackets indicated the anti-symmetric combination. And this box is not the box that Luke mentioned. This is defined with respect to the covariant derivative on the background. Okay, so this is the last thing I'll say in this section. In the afternoon, we'll start from here and derive the linearized Einstein equation and just mention the schematic form of the second order Einstein equation. Okay?
Okay. So when you showed that C can be written as G and derivative of H, that implies that H is a tensor in a
H is a tensor, yes.
Is a tensor.
Yeah.
And each term of H, because H is the whole or all the other orders of the perturbation. So each term is also a tensor?
Yes.
Oh,
Yep.
okay.
Yep. So they're all tensors that live on the background manifold.
Ah, okay. Okay.
Anything else?
In the proof there is a term that have a C and an able in the proof.
This one here?
Or in the second,
this one here?
the line, the other line, that.
Not this term?
The next line.
This term. This term.
That's term.
This one here.
This term. A C and an habla.
Yep.
And that term does not appear in the first line.
So this derivative is acting on everything in here. So you're going to pick up a term similar to this from this derivative acting on the omega. Those terms are going to cancel.
Okay.
So in the end, you don't have derivatives acting on omega. You only have derivatives acting on C.
Okay, one more announcement before we break for lunch. So we're supposed, you are invited to the social dinner on Thursday night, this Thursday. 7:30, the restaurant is Bovinus, it's a churrascaria. It's a self-service, so the dinner is by courtesy of ICTP. You pay the drinks. Okay, actually you have the food and one non-alcoholic drink paid by ICTP, and then you pay the extra drinks or the alcoholic beverage. Remember. So I will pass by a sheet in the afternoon, so you note down your name if you're willing to come, so we make the reservation. Okay, and we reconvene at 2:30. Okay.
Yeah, so that's always possible at one point.